Hello and welcome back to Virtual Thermodynamics. So we've been talking about thermodynamic cycles. In particular, we've been looking at examples of Rankine cycles. We started with a 4-component Rankine cycle that had a thermal efficiency of around 28%. Here the ideal efficiency, or the Carnot efficiency, was 55%. So we've got room to improve. We added a reheat to this cycle in the last example, and we increased the efficiency from 28% to 29%. But maybe there's things that we can still do to improve our efficiency. And remember, we like to improve our efficiency because it means that we save money and we reduce emissions. So we can think about improving efficiency by looking at our equation or our definition for efficiency. So we can think of efficiency as the energy benefit divided by the energy cost, where the energy benefit in this case, because it's a heat engine, is the net power divided by the heat in. But we also know that that net power is heat in minus heat out. So when we were talking about the reheat cycle, what we were doing, at least the way I think about it, is increasing that net power that we develop by getting a high pressure and a low pressure turbine. But today in regeneration, we're going to talk about reducing the heat input to improve our thermal efficiency. And that's called regeneration. So what we're going to try to do in regeneration is we still have a high pressure and a low pressure turbine. But what we're going to do is in between the two, we're going to bleed off some of the mass flow. So some small fraction of the mass flow comes off our turbine, or comes off in between turbine 1 and 2 here. So remember, this flow is still hot, but we've already extracted sort of the larger portion of the energy as the fluid was going through our high pressure turbine. So now we take Y percentage. So here Y is just some fraction between 0 and 1. And the rest of the mass, so if Y was say 20%, then 1 minus Y would be 80%. And 80% of that mass goes through this other leg of our cycle. Now in what we're calling the open feedwater heater here, the mass comes back together and all of the mass, or m dot total, goes through the purple part of our cycle here. So the idea of regeneration is to increase efficiency. We're reducing the heat that's required by the boiler because we're preheating the liquid that's moving into pump 2. We're increasing the average temperature of heat addition because the temperature that goes into the steam generator is now higher. And we're reducing the amount of heat that's rejected during condensation because we're taking some hot fluid out here at state 2, and some portion of the mass flow rate doesn't go through the condenser, and we're using that heat that would otherwise be lost to the environment to preheat our fluid going into the steam generator. So all of these actions are LORAX approved because we'll try to increase our efficiency to reduce emissions and save money. Now, in regeneration systems, we have 2 different types of feedwater heaters. So the first is an open feedwater heater. It's called that because what happens is there's this open flow inside the feedwater heater where our hot fluid at state 2 comes in and mixes with our cold fluid at state 5. I think of this as my grandfather used to have a sink that he would shave in that had a hot tap and a cold tap. He'd put a plug in and he'd let the hot and cold water run into the basin to get warm water. And that's kind of what we're doing in this open feedwater heater. Our closed feedwater heater works a little bit differently, where we have our hot fluid and our cold fluid, and they never touch. So here, the hot fluid moves in a heat exchanger where it's isolated from the cold fluid, and they transfer heat between each other, but they don't transfer mass. So in both cases, we have a diverted mass flow that goes on our red line. So the red lines look a little bit different here. We have the undiverted or non-diverted mass flow that's on our blue line. And then these two flows come back together in different places. So for the open feed water heater, it comes together in the feed water heater. But for the closed feed water heater, the mass flow rates come back together inside the condenser. And then after they come together, there's some leg of our cycle that has the total mass flow rate that goes through it. So first, I want to talk about an open feed water heater. So I'd suggest if you're going to do a problem like this on an exam, don't be afraid to bring some colored pencils or some crayons or even some markers to your exam so that you can draw colored lines like this so you don't forget that the mass flow rate is changing depending on where you are in the system. So in our open feed water heater, right, we're still going to look at thermal efficiency as being the benefit over the cost, which in this case is the net work divided by the heat in. So what I like to do is make a table like this that, so I can track where we are in terms of the mass flow rate that's going into each part, right? So I have the last column here is the mass flow rate at this state divided by the total mass flow rate. So the parts on the purple line get 1, right? Or this dimensionless mass flow rate is 1. They get all of the mass flow rate. The parts on the blue line get the diverted fraction of the mass flow rate. So again, if y was 20%, this would be 80%. And then there's some parts where I'm going to get so if I look at the open feed water heater, I've got at state 5, it comes in at this undiverted mass flow rate. At state 2, we get the diverted mass flow rate. And at state 6, we get all of the mass flow rate. So when I'm doing my conservation of energy in this case, I have to really be aware that conservation of mass is important here because the mass flow rates aren't the same everywhere in the system. So for this open feed water heater, if I look at my net power, I know that it's going to be the sum of all the turbine powers plus the sum of all the pump powers. Now I'm defining this as m dot times h in minus h out. So remember that the turbine powers are positive, that's why they're green here, and the pump powers are negative, and that's why they're red. If I'm drawing them on my TS diagram, I see that the turbines are producing power, and the pumps, there's 2 pumps now in my system, are consuming power, or the power goes in. So I have 4 different components that I have to do the first law on. But all of these components have the same assumptions in my first law, and they're going to tell me that everywhere here, the power for each component is m dot times h in minus h out. I add these all together, and I let the first law worry about the sign, so the turbine powers will be positive, and the pump powers will be negative. Now it's tricky here because now I got to remember. So again, if I'm using colored pencils here, then I can see back on my previous table that the mass flow through turbine 1 is the total mass flow. The mass flow through turbine 2 and pump 1 is the undiverted mass flow. And the mass flow through pump 2 is the total mass flow. So now I can divide everything by m dot, the total mass flow, because all of these things are a function of m dot, right? So I can divide both sides by m dot. So now my power becomes power per mass flowing through the system, and I get these as delta H's multiplied by some fraction. So now if I'm looking at how much heat is put into the system, in this case, unlike the reheat case, I only have one place where I'm adding heat, and this is going to be m dot times h out minus h in. I remember here that through the steam generator, in this case, I have all of the mass flow rate going through the component. So I get that Q in, that's little q in, so heat per unit mass flowing through the system is H1 divided by, or minus H7. So now I can put all of this together to get a thermal efficiency for open feed water heaters that look like this, right? And I can use this same general process for any kind of regeneration system or a system that has regeneration and reheat. It's just that my equation gets longer and longer as I have more components. Now the question might be, in a problem maybe you're given y, but maybe you have to find y as well. So if you have to find y, what you typically would do was look at a case where maybe you're told the net power in the system. And if you're told the net power, then our numerator here is known and we can find Y. You can look at a first law analysis on a feedwater heater. This is usually something you'll have to do in a regeneration problem, right? So if we do the first law analysis on a feedwater heater, if it's an open feedwater heater, we know that it's at steady state, that it's adiabatic, meaning that no heat is lost to the surroundings. It's passive, meaning that no power is generated or consumed. There's more than one inlet, but in this case, there's only one outlet. We can neglect the change in kinetic energy and the change in potential energy. And we find that the sum of m dot in h in is equal to the sum of m dot out h out. We can work this out because we know all what's going on in our system, and I can get an expression for Y. So that's sort of how we deal with open feedwater heaters. But what about closed feedwater heaters? Now it's important to remember here that the general process is the same, but the answers we get are going to be a little bit different. Right? So again, our thermal efficiency is the energy benefit over the energy cost, or net power over heat in. I'm going to, again, get out my colored pencils and try to see which mass flow rates are associated with which components. So here I have some that have different mass flow rates inside of them. So I'm just going to kind of section those off for now. I see where I have my total mass flow rate, where I have my undiverted mass flow rate. And then in my condenser, I see that I have 1 minus Y going in at state 3. I have Y going in at state 4. And I have Y going in at state 8. And I have 1 coming out at state 4. On the cold side of my open feedwater heater, I have all of the mass going in at state 5 and out at state 6. And I have the diverted mass, Y, going in at state 2 and out at state 7. Again, I want to find my net power. Again, I have 2 turbines, but now I only have 1 pump. So I can find an expression for net power. I can expand this expression by doing a first law analysis on each component. And then I look at what are the individual mass flow rates going through the 2 turbines and the pump. I can divide both sides by m dot again, and I have an expression for the net power per unit mass flowing through the system as a function of my enthalpies and of the undiverted mass flow rate. Thermal efficiency for the closed feedwater heater. We also need to find the heat in. So I look here again, there's only one place where we're adding heat, which is different than in reheat. All of the mass flow rate goes through this. So this just looks like heat addition in a normal Rankine cycle. And I get, again, little q dot in. And again, we need to find Y. So we can use sort of the same strategies where if we know the net power or if we do a first law analysis on the feedwater heater. So first law analysis on the closed feedwater heater will look like this, where we have that all the heat that's leaving our hot side of our heat exchanger, which is going to be m dot times Y. That Y should be outside the bracket. Should multiply by H2 minus H7. Oh, see, what I did was I separated this already. So I can get this expression if I look at all the m dot ins, right? So that's the total m dot in times state 5, and the diverted mass flow rate at state 2, those are the states that are coming into my closed feedwater heater, and the states going out of my feedwater heater, all the mass flow rate going out at state 6, and the diverted portion of the mass flow rate going out at state 7. So if I do that, then I can get an expression for Y. So I'll do an example here, finding the diverted mass in H6 in a closed feedwater heater system with the given state table. So I have my equation for thermal efficiency, which we just worked out. So this is a function of the enthalpies in the system, which I've been told, and of Y. So I know little w dot net. I know H1, H2, H3, H4, and H5, but I don't know why. So here, because I know little w dot net, I can find y. So now I wasn't told H6, but I know why. So I can do a first law analysis on the closed feed water heater, which we've derived already. I can cancel the total mass flow rates, and then I can find an expression for H6. I don't know H6, but I do know H5, Y, H2, and H7. So if I put all of that into my calculator, then I can find that H6 is 624 kilojoules per kilogram. So usually we try to ask these questions on exams so that you will eventually have to do a first law analysis on the feed water heater. And maybe you do it to find an outlet state, like in this example, or maybe you do it to find the diverted mass flow rate, Y. Thank you for joining me on virtual thermodynamics, and I'll see you next time.